We have to click another.
Click here.
But it's still not working.
Oh. It doesn't work right now?
You click another, you go into the camera.
Where? I'm confused.
We just tried to log in and it didn't work.
Okay, I see.
It did log in, but we were unable to access the code in the camera.
I see. But yesterday it works? Or?
Yeah.
Okay, I see. That's fine. Okay. Do I understand correctly that people usually start like past 5? Like I wait for 5 minutes, or should I start now? What's the normal way to do this? Start now. Okay. Sure. Okay. So welcome everyone again to the class. And one thing I totally forget to say last time is about how to scribe note. Let me. Where is? I guess here. So basically, most of the note that the task of scribe the note should be quite simple for this class, because actually I will try to make the bullet point note like this, and the task is really just to make it nice, like read nicely, and that's it really. Like make it not like this bullet point, and the way to go is that maybe I think you will need to book like which file. Like I will basically upload this kind of bullet point notes into the canvas, and you say, okay, which file you want to scribe, make it nice. All right. And if there are something like 15 people, then basically I suspect that you might need to choose like 1 or 2, at least 2. In the worst case, it will be 3 files. Yeah. So, and you basically, I think, can, for now, I think, put your name in this Excel file. Maybe say that, okay, like maybe I say, how do I need to log in. Okay. Maybe say like, okay. How do I access? So
I think if created this document correctly.
I see. Yeah. All right. Sure. Thanks. Sure. Maybe just write it like your name. I don't know. This thing should be quite informal. Scribe lecture 01 theme. Something like this. And where is this link? This link is in Canvas, right? It is like when you will see this link in Canvas. Yeah. Right. Any question about scribing? Okay, so we will continue now. So last time we talked about expander, introduced some notion of expander, specifically conductance. And conductance is defined like this. Conductance of a cut is a number of edges over the number, like over the volume of the set. So if you have a set S, you count the ratio between edges going out of S and the volume of it, assuming that volume is on the smaller side. Yeah. And the volume, what is volume? Volume is just summing over all degree, which is essentially summing over all degree of node in the set, right? Which is essentially the number of edges incident to the set. Okay, and can someone remind me, remind everyone? We kind of give some characterization of what it means for the graph to have high conductance. Yeah, can you tell?
I just had a question. Does the degree include the deleted edges? Or,
No, this is really just you have a graph. You just look at the degree in the original graph. Yeah.
Oh. Okay.
Yeah. Yes.
High conductance of the graph is kind of like robust against the edge deletion.
Yes. Right. Yeah. High conductance mean is robust against edge deletion, and quantitatively we show this. That is, if the conductance is at least 5 up to some constant, then when you delete any edges, any set of HD, then the total volume of the thing that you disconnect from the graph is going to be small. It's going to be like something like D over 5. That total volume is kind of small. Okay. And now,
And if you assume like the original graph is connected.
Yeah. So at least if phi is more than 0, yeah, then it's going to be connected graph. Okay. So yeah, I should say that phi is at least 0. Okay. So and now we stopped last time at this point. We want to prove that using the connection that we, like the characterization that we discussed above, we want to show that, okay, suppose that the graph is a phi expander and phi is more than 0. Yeah. Then we want to show that without any processing on G, and given any set of H deletion D, if you want to check if two nodes S and T are connected in the graph after deletion, then what you can do is just, you can do this in time which is proportional to D. Yeah. D over phi. Right. And by the way, if D is empty, then you don't need to do anything. And that is trivial because the graph is already connected, you know everything is connected to each other. Okay, but what if D is not empty? What do you do? So let's discuss the idea before going to the proof, right? Imagine that you have an expander G, and let's say I delete some H D. Yeah. And what do you have? You have that after deletion, the graph gonna look like this. It might disconnect, so G minus D gonna maybe it look like this, and it might have some small connected component such that this total volume is at most D over phi, right? So what you're gonna do if you are, this we know, this structure that we know gonna happen. So now suppose that you are given S, you're given S here, and maybe you're given T here. Then we know, like, what do you think we should do actually? What should be the algorithm to check if S is connected to T or not?
Maybe like breadth first search, but you only need to check like volume number of edges.
Yeah, thanks. So the idea is really just try to do some breadth first search, right? Suppose you do breadth first search from S, and if S is in this small component, you will get stuck very fast. How fast? You will need like the volume that you will explore is gonna be at most D over phi. So you will get stuck in time, something like D over phi. If S is in this small component, but if S is in big component, you will not get stuck. But you know that if you don't get stuck within this time, you will be in a giant component here. So what you do is you really just explore for a while, do breadth first search, count the volume that you have seen so far, and whenever the volume is more than, if the volume more than D over phi, then you just stop, because you know that you are in this big guy, big one. And that's the idea. You do the same for T, right? If T is here, just check if it is in the small component or a big one. If it's in the big one, you also explore for like a small volume, and you just stop. And if both of them are like in the big, like now you know which component of S and T are in. Okay, yes, question?
So, I have a quick question. So you said, for example, we do a breadth first search from vertex S, and then if if the edge that we go over is larger than D over phi, which means, okay, S is actually in the larger component.
Yes.
But that's still possible. For example, my T is in the smaller component.
Right.
So how we,
So what we are doing really is just to identify which component S is in, and then identify which component T is in, and then you compare if they are the same component
oh, so we need to do like breadth first search on both.
from both S and T.
Oh,
Yes.
Wait, is it possible that you get always like small components? Wasn't this like one of these cases? Or forget it?
So all of the, well, you know, right? If you are in the small component, the total volume even here is small. So each of these small component need to be small. Otherwise, you know that there is just, there can be at like at most one large component. Like so recall that when we talk about here, small components means that the guy that have volume less than half. So the large component, there is only one large component. Okay. All right. So any question about this algorithm?
Can it be the case where there's no large component?
It can be the case. There is no large component, but that can happen only when you delete really a lot of things in the graph. So from here, it can be the case that there is no large component, but then if no large component, then actually D need to be at least 5 times the volume of everything. Right, just because it means that if there is no large component, it means that the total volume of this thing is everything, right? So if there is no large volume, D is big, but if D is this big, then the time of this time is already like everything in the graph. So that is kind of a trivial case, a corner trivial case.
So here we assume phi to be a constant.
We don't assume phi to be a constant.
So what if phi like depends on n?
Yeah, phi can depend on n, right? So here, well, there is just no place that I assume that phi is a constant at all. What I mean is just to address your question again, if there is no large component, then we know that D is bigger than this. But then this statement just said that you just need something like D over phi, which is volume of everything. And that is kind of trivial. Does it make sense? Okay. Any more question about this theorem? Yes, please.
so what if S and T are both in the smaller component, but in the smaller component, it's also like you're like in a separated, like a smaller component, like it could
Sure.
be separated, right?
Yeah,
But
yeah.
that would take longer time than D over.
Phi. So by the way, this is like a call phi or phi. I don't know how, like people call phi or phi. But anyway, so if S and T are in the different small components, right? Well, you explore from S, you identify that it's here. You explore from T, let's say T is here, T is here. Then you identify that this is another component. Then you know that they are different components, really. So, like,
So for example, both of them get stuck.
yeah.
Before they find, like getting stuck by d over phi before defining the path between them, and then we just stop, basically.
If you want to find the other
They can't go till d over phi because of total volume itself is 0.
Right. Like, we know that this total thing in total is d over phi. Yeah. Thanks. Yeah. More question? Okay. So next thing is that I just want to prove quickly that the expander is not just robust against deletion. It's kind of a good cluster in the sense that it has small diameter. So what do I mean by that? So the diameter of the graph really is just the maximum distance between any two nodes. Okay, so you are like maximizing overall U and V, how far you need to go from U to V, maximizing overall pairs of nodes. That's the diameter of the graph. Yeah. And now we want to show that any expander, any phi expander will have small diameter. By small, I mean something like log m over phi, where m is the number of edges in the graph. Okay. So it cannot be that the case that you have an expander, but there are some pair of nodes that are far away from each other. Everyone is close to each other in expander. Okay. So how do we prove this? The proof will use a ball growing argument, and this will be used many times in this class, actually. So let's prove it. The idea is just this. Let me first define some notion. So let me call it B of S and R. This is just a ball of radius S, of radius R around S. That is, it contains all nodes, such that the distance from S, all node U such that the distance from S is at most R. So pictorially, you have S here, and look at the radius R. So then everything here is a ball of radius R. Okay. And now let me tell you some idea of the proof first. Because this graph is an expander, what do you know about each ball? Like, we know that, look at this ball, right? If in expander you have a lot of edges going out of this ball, which means what? Which means that if you look at the next ball, B of S R plus 1, this ball should be quite big. Like, it should grow quite quickly compared to the ball in the previous radius. and how fast it should grow. So the ball of radius r plus 1 is really the ball of radius r union with kind of, let's say, to be more precise, the volume of this ball is what? Is the volume of the ball of radius r. And then you will count in addition these edges, right? So it's gonna be at least, yeah, at least this. And you know that this thing is quite big compared to the ball, compared to this ball. How big is this? Can anyone tell me how big is this in phi expander? Right. So this thing is at least phi times this volume, right? So it means that this thing is really like, it grows by like 1 plus phi times the volume. So when you increase the radius by 1, this thing grows multiplicatively. And if you think of phi as some constant, how many times this can happen?
Log m.
Right. This can happen only like log m time, because the total volume of a graph is m, and if you grow multiplicatively every time, that is just gonna stop before it's like more than log m. So that's the idea. But we need to be careful about this argument a bit, because here this inequality only holds when we are on the smaller side, right? So that is why I need to be a bit careful, and let's look at the definition here. It's just the definition that take care of this kind of this point. So let R of S be the radius such that is a radius such that it's the first step where the volume is more than half. But if this is -1, it's still less than half. Okay. You define the same thing for RT. Okay. So now I have a graph, and I have S and T, and I have something like RS and RT. And note that this ball must intersect. The ball here must intersect. So note that this is not empty. And why is that?
Because we are saying the next one only the volume is more than half.
Right.
Or both.
Yeah. The volume of both are more than half. Right. So there are two sets that in total the volume is more than half. So they must intersect at one point. So this is the intersect. Okay. And just because of this, we already know that the distance from S to T is at most this, RS plus RT. And we just need to prove now that both RS and RT must be small. And to prove that, it's just use the argument that we just discussed. Because, for every for every R which is less than RS, each of this ball, they grow multiplicatively at each time. So we have that ball of the ball of SR is at least it grows by this multiplicatively, and so it must be at least 1 plus phi to the R. And then so this is just the thing that I just discussed here. And any question about this?
So when R equals to 1, it actually goes, I mean, it's probably like off by 1. It's like when R equals to 1, the definition.
Yeah, maybe it's, you're right, thanks. So,
Yeah, but this
yeah,
is way easier.
thanks. Okay, this should be R minus 1. Yeah.
Why?
Why?
I mean, when R is 1, you include yourself and your neighborhood. Yeah, so if you only have one edge, then
Yeah.
require there should be, I mean,
It can be the case that the volume of B of S1 is 1, right? But anyway, this is corner case. Let's just ignore it. I will likely throughout the course be sloppy about this corner case. Yeah. The important thing is that you get the idea. So, okay, now that we know that the ball will grow multiplicatively by a factor of 1 plus phi, then we just need to calculate, make this idea precise. So 1 plus phi to the R S is around e to the phi RS. By the way, this is, if you haven't seen this inequality, just note it down that this is a very important one to know. That is, for all x, 1 plus x is around e to the x when x is less than 1. Yeah. Okay.
Sorry about that. I think it's still R.
Oh, really?
Yeah, if you just plug in the distance. So the thing is the ball S with distance 0 is actually includes the degree of that vertex as well. So
I see.
yeah, sorry.
I will just believe that. Okay. Anyway, we know that this thing is around e to the phi RS, and we know that any ball is at most the volume of everything, which is 2m. Then comparing these two together, it implies that R of S is at most log of m over phi.
Is it not volume by 2?
Well, yeah, but yeah, it's also at most volume too. Yeah, so. I mean, this is at most total volume, right? Okay. So we know that Rs is small, Rt will be small too, by exactly the same argument. So that's why we conclude that the distance between S and T is log m over phi. And this is true for every S and T. So diameter must be at most this. All right. Question? Okay. Oh, yeah. can you give me a graph with small diameter but have low conductance? Who said this again?
Complete binary tree.
Yeah, right. A binary tree, for example. Complete binary tree. What else?
2 stars and then 5 short path.
Yeah, great. Or like, and this part maybe is like length 2. Okay. Thank you. So we know 2 things. First, expander are robust against deletion. Second, it has small diameter, but there can be some low diameter graph that is not expanded to. And let's look at some non-trivial example of expander. Like so far, we have seen actually 2 examples of expander. One is complete graph, but that is totally not surprising. It's just the most well-connected graph. So, yeah. And also, we also have seen that stars have high conductance. But that is also not that surprising too, because there is just one guy that have very high degree. So it's kind of very well connected. But the nice thing to note is that like this is like something that is surprising or not maybe, but there can be the graph that have very small maximum degree, not like star, yet it has high conductance, like constant. So the point is that can be very sparse graph in the sense that like it's everywhere sparse, low degree everywhere, but they are still very well connected. And give you some example. The first one is hypercube. So imagine that each node in the graph is like a bit string. Okay. And you connect edges. You add an edge between U and V if the bit string of U and V are the same, except at one entry. For example, in 2 dimension, like when this dimension is 2, then you have this graph 0, 0, 0, 1, 1, 1, 1, 0. So this is hypercube. And in 3 dimension, it's gonna look like this. And in 4 dimension, it's gonna be harder to write, but it looks like this. And one can prove that I might add this into the last part of the course. I'm not sure, but it can be proved that the conductance of a graph, when there are n nodes here, then the conductance is quite high, like 1 over log n. So not constant, but quite good, like 1 over log n. Okay.
In this height,
This is tight. Yeah.
about 1 over log.
Yeah, this is really theta. Yeah. There are like a more example. You can draw a grid. Basically. So each node is like you have like a grid of length n by n. Each node corresponds to a number between like x and y, where x and y is between 1 and n. This is not something that you need to remember or anything, by the way. I just want to say that this exists. Yeah. And it's quite interesting. And yeah, and now instead of connecting each node like a grid, right? You connect it in this way, like X and Y will connect to this guy. And this thing you compute and then you mod n. All right. So this is like a two neighbor of X and Y. And there are another two, and another two. And when this is an example when n is 3. So there are like a nine nodes. And you cannot see that, okay, it's kind of, things are jumping around basically. And they are well connected. Like the proof is very non-trivial, but like it used some deep math, which you can look at in this lecture note actually, if you want to look at it now. Also, there is another one which is very simple to describe. That is, take any prime number, p, and then draw it in circle like this. And basically, everyone have 3 neighbors. So, like a node 20 is connected to like 21 and 19. So with only these two, they look like a cycle, right? But you just add another guy, which is an inverse of it in this finite field. That is like, for example, 20 is connected to 3, and 20 times 3 is actually 1 mod this. Like this is example when p is 59. Yeah. So it turns out that this graph is an expander too. It is actually like the expansion is constant. Yeah. So there are like a field of study actually. How can you generate expanders from some algebraic object? This is very nice and deep, but this seems like expander must be very special graph, but that's not really the case actually. It turns out that almost all graphs are expander. So what do I mean by that? I mean that if you look at a random graph, they are expander with high probability. Which means that if you look at the set of all graphs and you pick one out like randomly, most likely that graph will be an expander. Okay. So, and there are several models of random graph. One which is very simple is the simplest one is Erdős-Rényi graph, GNP. How do you define this graph? So you start with a graph with n nodes, and for every edge, you add an edge between u and for every pair of nodes, you add an edge between u and v with probability p. Okay. And for example, and let's say that look at p when p is something like log n over n. How does it look like here? So what is the expected degree of each node? Log n, right? The degree of each node will be something like log n. And actually with high probability, it will be around log n. It will concentrate. And in your homework, actually, you will show that this graph will be an expander with high probability. So this graph have maximum degree log n with high probability, and you can show easily that just use some Chernoff bound. This is like a way you need to recall how to use Chernoff bound, but this will have high conductance. Yeah. So it means that almost all graph that is very sparse, something like maximum degree log n. This is like they are very well connected. There are some other kind of random graph that yes, please.
At what point does the conductance get high enough that you can say like this is an expander, or is it just kind of like a feeling?
Very good point. So actually, maybe I will put this into the homework too. That is, if P actually is kind of less than log n over n, think of it as maybe log n over 1000 n, something like this. Then you can actually say that this graph, not just that it's not expander, it will not be even connected. So it's likely that there is some singleton node that have no edge with anyone. But it turns out that when you look at the point when the graphs start being connected, then they are expanded immediately. When the graph is random from this model. And when P is larger than that, then it's even more connected. Even more.
Is there like a line or some sort of threshold of the conductance that tells you like this is now an expander, or is it just kind of like this is good enough?
So it is really this threshold. So the threshold of when this is P and the threshold is really at log n over n. Everything here not connected with high probability, and here they are connected, but not just connected. The conductance is going to be constant. So it's really a sharp threshold. Yeah.
Maybe a question was like, for any fixed graph, there's like, when you say that like, for example, the conductance is at least 0.1, does that mean that graph is an expander? Like, would you define it as an expander?
For any fixed graph, sorry, I'm not sure I understand the question actually.
So the question is like, what is the minimum conductance for which you would call a graph an expander?
Oh, I see. Thanks. Okay, that's the question. Okay, so it depends on people. So in many times, people will call a graph an expander if conductance is a constant. It doesn't depend on n at all. But to me, like and many people in graph algorithm, fast graph algorithm, when the conductance is like 1 over polylog n, that's kind of good enough. We call it expander. Yeah. Okay. And so this graph is an expander with maximum degree, something like log n. But you can generate even sparser expander. If you take perfect matching. If you take a graph with n nodes and like you look at some random perfect matching. So random perfect matching is like it's just n edges, right? And but you pair them randomly. Take a random perfect matching, but takes like 20 of them. Union that, it turns out this is expander too. And note that in this graph, if you have 20 matching, the maximum degree is going to be 20. So it's even sparser, but also have high conductance. And by the way, when I think about expander, I usually think of this kind of graph, where it's actually really sparse, but like no high degree node, but are well connected.
What is the relation between the order of 1 and omega of 4? Like, is it almost the same constant?
Oh,
1 with C and C?
you mean this and this?
Yeah.
I'm not sure actually. I'm not sure. Yeah, maybe if you look at this lecture note, you can calculate it. Yeah. Okay, so that is, so far we have talked about conductance only. I want to mention other notion too, and that is vertex expander, vertex expansion. So just recall that conductance is about ratio between the edge crossing the cut and the number of edges disconnected by the cut. That is conductance, right? We can just talk about vertices too. Try to define something similar, but for vertex, right? So to do that, we need to talk about vertex cut. So what is vertex cut? Just to remind you, when you have a graph, and when you partition the set of nodes into 3 sets, like on the guy on the left, and the guy in the middle, and the guy on the right. And if there is actually no edges connecting between the left and the right, so that is, if you delete the separator guy in the middle, then the graph is disconnected. That is when you call this. That is when you call LSR is a vertex cut. Okay. That's the definition. And now it's quite natural how to define vertex expansion now. It's kind of just how many vertex you need to delete compared with the number of vertices that you can disconnect from a graph. And which is just the ratio given the vertex cut LSR. It's just the number of guys that you delete, and like you ask how many guys you disconnect or you have removed from the graph. Make sense? Okay. And then similarly, to define vertex expansion of a graph, just take the minimum the minimum vertex expansion cut, and that is the vertex expansion of a graph. Okay. Yeah, and one can like say that just similar to what we have seen before. A cut is a vertex 5 vertex sparse if vertex expansion is small. Otherwise, and a graph is a vertex expander, 5 vertex expander, if there is no 5 vertex sparse cut. Okay, first question. If a graph have maximum degree constant, say 10, can someone tell me why vertex expansion and conductance must be within some constant, like 20? They must be kind of the same. in particular, if you have any cut, any 5 sparse cut in some graph, which is any 5 sparse cut, any 5 edge sparse cut in one graph, you can find 5 vertex sparse cut in another graph. Why is that the case?
Because the maximum degree is constant.
Yeah.
Because the volume will become at most constant multiplicative of the vertices count.
Right. Yeah. So the idea is kind of simple. Yeah. So if let's say you have 5 edge sparse cut, so this is like the number of edges is small. Oh no. Then you just kind of, if you just take the end, if you just take the end point of these edges as your S, that will be a cut. That will be the vertex cut in the graph too, right? And the ratio of the number of edges over volume and the ratio of this thing will be within constant because the maximum degree are like is constant. So that's why the vertex expansion and the conductance of this cut are kind of the same. Right?
Yeah,
Yes?
so if a cut S is fixed, but L and R is not fixed, so how can I define the vertex, conductance of the vertex cut? Only depends on S.
So you can take all of the edges incident to S. And so maybe like this. Oh, sorry. Shoop. So basically you ask, if you have a vertex cut, how do you define an edge cut? Basically, and
Actually, my question is about the definition of the vertex conductance. Yeah, your definition only depends on S. But if you keep a fixed S, if you remove S from this graph, there may be lots of connected components. So L and R is not fixed.
yeah, but okay. So that's a good point, I guess. So if you have S, and let's say you delete S, and maybe there are like some, after you delete S, it can be many connected components after deletion.
So will you choose the L and R that maximize the conductance?
Yeah, we will just choose L and R to maximize the volume. So that will work, yeah. And maybe take this as an exercise how to make it formal.
It's also defined in such a way that L is the smallest component and R is the rest of the graph. So that is how it is defined.
Yeah.
L is the smallest one, so in that case.
So you need to kind of choose L and R so that both of them are like they are most as balanced as possible.
Balance?
Actually, yeah.
Okay.
Because if they are balanced, you get like smaller expansion.
But the worst case, we will choose the maximum like parity. Right?
Sorry?
So, but in the worst case, so we have to choose L to be very small and R to be big, so we actually get a bigger conductance.
So we take the minimum.
Yeah, we
take the minimum. So
we can consider the minimum is a independent set of vertex, and the other three, for example, in this graph, let's say undecided.
Yeah, let's let's take a short break because I need to restart my computer. Because somehow my pen doesn't work anymore. Just 2 minutes break. Okay, actually, I have a question for you. Can you give me one example of a graph such that it is a very good edge expansion, a very good conductance, but it is very bad vertex expander? Very good.
That was the first example I thought of actually when I was reading the definition. I was like, oh, that's weird.
Right. And how about another way around? Is very good vertex expander, but very bad edge expander, very bad conductance.
So is it like this? Two vertices and all of them intersecting? That like two stars combining in the middle with the same?
Well, okay, one sec. So now it comes. Let's discuss this a bit. The graph that is very good edge expansion, good conductance. I will likely say edge expansion and conductance interchangeably. All right. It has very good conductance, very bad vertex expansion. So that is a star. Because you just need to delete one node and you disconnect. You can take L to be this and you take R to be this. And that has very small vertex expansion. Now, on the flip side, very good vertex expansion, but bad conductance. And Chaitanya, what did you say again?
Two vertices with like two stars with the same set of neighbors.
Oh, something like this. So one thing to note is that this graph, so is it good or bad actually? I mean, if you delete these two nodes, then you disconnect everything, right? So it's not a good vertex expander.
What about two complete graph connected by a perfect match?
Yeah. So what about two clicks? And connected by what?
By a perfect match.
Yeah, good. By a perfect matching. So this is so this is actually correct. So it is very bad. It has very bad edge, very bad, like very small conductance for sure, right? Because there are only n edges here, but you disconnect like n square edges from the graph. And also it has good vertex expansion. So why is that the case? So basically, if you take any small set here, then the neighbor is at least this for sure. But if this is like, okay, let me do this in maybe exercise session, so that we can go further. But how you think about this? Why this have a good vertex expansion? Okay. And there are more things to say about vertex expander. Like a lot of things will transfer that we have discussed before about graph with high conductance. So basically, if you have a graph and it is a good vertex expander, it is a phi vertex expander. And now if you delete a set of nodes. You can also check if S and T are connected fast. And the time to do that is something like D over phi, but square. Any idea how and why this is the case?
Because maybe it's as similar as removing edges, but we are removing all the edges that are possible between the subset D with itself.
No, we will need to kind of we need to use the fact that the graph is a vertex expander somehow, right? Yes?
Just the same idea as the edge. The edge example. Like, the only difference is the power 2, right? So when we explore vertices, there involves like, if there are n vertices, there are n squared edges we should to explore.
Yes, that's the idea. So let me just rephrase what Tian just said. So the idea is that you can prove similarly that if the graph have good vertex expansion, then there is the same characterization that if you delete D nodes from the graph, then you can disconnect something like D over phi node. The total number of nodes that is disconnected from the graph is D over phi, right? And now, imagine that you delete D nodes here. What will happen? So you might get a bunch of small connected components. Each of these, like all total of this, is something like D over phi nodes. But what if I just do exactly the same algorithm that we have discussed before? I just explore the component until I find the O phi node instead of explore until I explore like a DO file volume. Now the threshold is the number of nodes, not the volume, right? But how does it take to explore the graph with DO file volume? DO file node. So that will, if you try to explore DO file nodes, then that can be done in time, can be done in time, DO file square time. Because the number of edges inside this node is going to be at most this thing square, right? So this is something that that is a trick, basically, how everything follows. So we will basically tomorrow, we will try to make this thing formal. And the next thing is, okay, it also has small diameter. Okay. And this will just use the same kind of argument. You can try to do it yourself. Or we will do it in the exercise session. Okay. And before we stop, I will tell you about maybe there are more this is vertex expansion is just one example of another way how to measure expansion. There are more general way to measure expansion. For example, we can define D as a function, which is a demand function over vertices. And let's call D expansion of a cut. It's really just, we define it to be the number of edges crossing the cut and the ratio here. Instead of volume, we just put it to be D of S, where D of S is just summing over all D inside the set. Okay. This is just definition. And the expansion of a graph is just you're just minimizing overall cut, such that D is not the D of S is not trivial. It's not zero or everything. Okay. Actually, first question. Suppose that I define it like this. That is, if I define D of S to be 1, if there are two nodes, S and T, if I define D of S and T to be 1, and D of everything else to be 0, then what is this thing?
What is D of S of sum of
The middle cut, it's like a middle cut.
Exactly. So that is exactly the size of the ST min cut in the graph. Why is that? Because when is it the case that the D of the set S is not trivial? It's only when the set S contains only S or contains only T. It's a cut. It's a ST cut, right? And we want, here it just means that we minimize over our ST cut. Minimize, what do we minimizing? We minimize the size of the cut over 1. So that is the size of the ST min cut. And also, okay, and conductance is really just the expansion when the function d is the degree, right? And now people usually consider this thing called d-unit expansion. That is, d is defined to be 1 for all nodes. Okay. And sometimes they just call expansion. And this will, what does it measure intuitively? It means that it measures like how many edges do you need to cut so that the number of nodes is disconnected. Compare the number of edges with the number of nodes that you disconnect from the graph, right? Make sense or not? Yeah, so when I define the set, the demand function d to be just all 1 on every node, right? Then this of d unit is just the number of edges minimized over this. And that's what I mean by like, we kind of, so this thing basically measure the ratio between the number of edges that we cut with the number of nodes that you disconnect from the graph. So it's just similar to conductance, that you compare the number of edges you cut with the number of edges you disconnect. Here is just number of vertices you disconnect. Yeah. Any example of the graph? Can you tell me an example of a graph where this thing is big, but it has large diameter?
Grid?
Yeah. Is it? No. Grid is small, right? So this thing is like a 1 over root n. So I think I will not tell you, and we will see tomorrow. But let me tell you about what will be in the next week. So today I hope that you kind of get an idea of what is expansion. There are many variants of expansion, but maybe the key notion of expansion that we look at in this class is conductance. The first thing that I tell you. Next week, I will tell you how to compute this number, how large is the conductance of the graph. It turns out that this thing is hard, is NP hard. You cannot compute it exactly, but we will see how to at least approximate it. So which means that if you can approximate this, you kind of, given a graph, you kind of know at least if it is an expander or not up to some extent, right? So we will see how to do this. Might take a week, but it turns out that the algorithm to compute whether to approximate the conduct center graph have very nice connection to one field of the math called metric embedding that have nice connection to functional analysis or something like that. So that is next week. And tomorrow, I will tell you about some exercise here. So see you next time.
Thank you, sir.
Sure. Yeah.
Do expanders ever deal with sort of like clustering?
Yes.
Yeah.
Yes. So like at some point in the lecture, I will tell you like given a graph how to decompose it into expander. This is really related to graph clustering.
Yeah. I'm doing like some stuff for some research work with a bunch of like tessellated hexagons. They're kind of just like neighbors connected to each other. And I'm trying to like cluster them somehow, I guess.
I see. Yeah. So maybe in your field, I'm not sure if you have used something called spectral clustering or something like that. That is really like very super related to expander.
Okay, spectral clustering.
Yeah.
Okay. Yeah. Thanks.
Sure.
Yeah.
Hey.
I have a question regarding previous content.
Sure.
The first question maybe the trivial is about this one. If we cut a set of the edges, why does C just contain FH of the edges?
I mean, this is the property that they hold that it holds.
Okay.
Yeah. So we try to consider that this is a graph that this thing holds.
Oh, okay.
Yeah.
I just didn't have this example.
Yeah.
It's a matter. And another question is
It's just that later we show that any expander will satisfy that property.
yeah. So another one is the